Good morning, everybody. So let us start our lecture this morning. Today is October 19th, and we are in the last half. Actually, we have covered 60% of our course. Let us see our schedule first. Okay, so in our last week, we discussed recursion and recursive functions. When a function calls itself, that is called recursive function, and the process is called recursion. Okay, like factorial, finding factorial of a method of a number is an ideal example of a recursive function, a recursive process. Okay, so this week we'll discuss trees. Okay, so if you go to D12 and in the content tab on the left panel, you will see our slides. So lecture materials, so 16 trees. So this is one. So chapter 10 in the book is trees. So let us open the book also. So chapter 10. Chapter 10 is all about trees. So tree is a data structure. Okay, so trees, there are different kind of tree type data structures. So we call these trees. So in real life, for instance, this is a tree. It has a root and it has some branches and sub-branches, sub-branches, and very top level we have leaves. The tree has leaves, right? So but in our data structure format, we will see the picture is upside down trees like this. So in the root will be on the top, and then all branches will be down. So here, like a root, 14 is a root, 17. This side is left side is a branch, and right side is a branch. So on the left side we call left subtree, and the right side we call right subtree. Okay, and each is the entire tree is built up with some nodes. Okay, so this is a node contains value and link to another node. Okay, so this is a node, 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 and there are some empty nodes. So empty nodes are not shown over here. Okay, so this is a tree. So there are different kinds of trees. We will discuss this. Okay, so what I like you to read through this book at least one time, please. So then you will see there are some terminologies, like very simple definition with examples and something, and then I think you will be familiar with most of this. But we have our lecture slides. We will go through our lecture slides. There has coverage of most important topics or most important items. Okay. So this in this week, our goal will be to familiar with different kind of trees, and then tree structures, and then tree terminologies, and then especially we will be familiar with BST, binary search tree, and traversal operation, of tree, and also you will see insertion and deletion operation of BST. Okay, so please read through these books, then you will get more important, more so all about in detail. So I will make a quiz. Okay. I'm making them. We have maybe 3 quizzes so far done. So by this weekend, I will post another quiz, and that will be due next week. By this week, I will post another quiz. Okay, so if you go through our slides, so you just download the slides. I have already downloaded it, and this is it. It is about 48 slides. Okay. So let us go through these slides. I have also my own slides, but if needed, I can go with this. Okay. So the tree, as I said, is a data structure. Then the question is that what kind of data structures and what kind of data structure a tree is. We have already seen various kind of data structures, right? So starting from an array, then linked list, stack, queue. We are familiar with these data structures. Then what is different in or special in tree? Actually, the data structures so far we discussed: array, list, stack, queue. All of those are called linear data structures. So linear data structures, that means a data repository. These are the data structure that where data are stored in sequential order. That means there is a first element, second element, third element, etc. Okay, and we know that in an array, elements are accessed through index, right? And in linked list, stack, and queue through link. Okay, so unlike these data structures, trees are non-linear data structures. So non-linear data structure means that data are not stored in sequential order. So stored in non-sequential order. Okay, so then what is how the data nodes are connected? They are connected in some other different fashion. So you will know this. Okay, so there are two main non-linear data structures that are trees and graphs. So at the end of this semester, we will discuss graphs. Okay, so now we will, this week and next week, we will discuss also trees and binary search tree, and then also heap. Heap is also a kind of binary search tree. So this 3 weeks, actually, we will discuss trees. After that, we will discuss hash table. Hash table is a different kind of data structure. And then we will go through graphs. Okay. Okay, quiz 4 is not uploaded yet. I will upload quiz 4 soon, maybe today or tomorrow. Okay. So please, first of things that remember that a tree is not a linear data structure. That means in a tree, the data elements do not come one after another sequentially, do not come sequentially, non-sequentially. Okay, so there are some common words. Okay, so common, these are called tree terminologies. Actually, the common terms that are widely used for tree operation and study. First of all, a tree consists of a set of nodes. As we have seen that in the linked list, it's structured with a set of nodes, right? So node, what is a node? A node is an item or say an object in object-oriented programming. I'm sorry. Dr. Daniel for I'm sorry. So a node is an object, we can say, in object-oriented programming that contains some data value and link of another node. So in a tree structure, the node, the link, we will say is. Okay, and so if there is no A's, so that means there is only one node, and that is only is called a single node tree. Okay, and the root node, that is called the root node. Okay, so these are the three terminologies: node, A's, parent node, child node, leaf node, siblings, ancestor, descendant nodes, and subtree. Okay, so let us give an example for this. Okay, and there are also some other terminology. These are called tree properties. For instance, degree of node. Okay, degree of a tree, depth of the tree, height of a tree, height of a node, ascendant of node X, this ancestor of node X, something like this. Okay, and then we will come this. Maybe we'll revisit this again. So let us go. Let us see this. An example. Now here. So let us draw a tree first. So here, if we draw, this one is node. Okay, and for all nodes, it is assumed that there is a null. There is a null. There are one or more null. So null. Children. Okay, and the connection, if this is not null, or even this is there is another node. If this is a node, whatever value it is, either null or something, the connection between one node to another node, this is called an edge. This is edge. Okay, and this is called parent node. This is child node. This is child node. This is left child node. This is right child node. Okay, and so by default we say it has everything has null node. So actually, if there is nothing, no more node, like this is a node, right? This is parent, this is left node, this is right node. So, but this has no real node. These are, maybe if it is, then it is null. So then, if there is no actual real node, real children, then this is called leaf. Okay. This is called leaf node. This is leaf node. This is leaf node. Okay, and it may have some other branches. Okay, some other branches. Okay, so this is called left subtree, and this is called right subtree. And siblings, these and these are siblings. These are siblings. Okay, like a parent children relationship. And this is a path. This is called from starting from root. This is root. Starting from root to level. Okay, this is called a path. So this is called ancestor nodes. Wall nodes on the path from current node to root. If you say this is my position is here. So from here to this path, all nodes, these are called ancestor nodes. This is ancestor and this is ancestor. And if this is my or any of these is my node. Okay, so from here to down to leaf node. What is leaf node? If a node does not have any more children, then it's called leaf node. So the down is called descendant nodes. Okay, so one thing you can remember that down, whenever you say down from up to down, then descendant. Okay. And this is left child, this is right child, this is left child, this is right child. Maybe this is middle child, this is right child. A tree may have, a node may have two or more, one or more children, child. Okay. We'll see this more in detail. But does anyone has any questions so far?
No.
Okay. Let's go to the next slide. Okay. So these are the common terms. These are very simple. If you read please one time, then you will understand. So degree of a node is a number of its subtrees. Degree of a tree is the maximum value of the node to all. Let me go to the next slide. Next slide has some picture. If you have a tree in hand, then we can explain this better. So degree of node D. So D is degree of node. It says what is the degree of a node? Is the number of its subtrees. So how many subtrees D has? The left side left one, right side one. So the degree of C will be 3, right? This is 1, 2, and 3. The degree of A is 1, 2, and 3. Okay. So then degree of the entire tree is the maximum number of nodes. So the maximum it has 3. But instead, this is a max of 0, 1, 2, 3. Why is it 0? But this one does not have any subtree. This one, K, L, M, M. This does not have any. These do not have any subtree, so they have 0. Then 0. Then this has 1. So H has 1. So this is 1. And E and D has 2. Also B has 1. Okay. And E and D, these have 2 subtrees. And then A and C have 3 children. So this is max of 0, 1, 2, 3 is 3. Okay. Okay. So the height, so for instance, here we'll see depth of a tree is 3. So how many? 1, 2, and 3. This is path. Maximum path is the maximum number of path is the length of the path is height or depth of the tree. So if we say descendant of node C, descendant of node C, descendant is down, right? Descendant of node C is the set of F, G, H, and also M. Do not forget to include M, okay? So descendant of C will be F, G, H, and also M. And ancestor of M will be starting from here to go all the way to root. How many nodes we have on this path? We cross this, how many stations, for instance, through this path, okay? Or nodes, so H, C, and A. Or you can say A, C, and H. Okay. So the path to a node M equal to A to C, and then C to H, and H to M. You can say this way, or if you have path number, for instance, if you have path number like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then we will say 2, 7, and 12. 2, 7, and 12. If there is a path number, then we can say. Yeah. So let's remember that the node, the root node, does not contain any parent. So here, in tree terminology, you do not see any grandparent, any terminology named grandparent. Okay. So is everybody okay? Has anyone has any question?
No.
Okay. These are simple. I think if you took 1322 our course, we covered some of these in 1322. Okay. So as I said that we say trees in general, not it's plural, not a singular tree. So because there are different kind of trees, there are different types of trees. Okay, one is called binary tree. So binary tree that each node can have maximum number of 2 children node, child node. Okay, binary means bi means 2. If a node has 2 maximum, either 1 or 2, 1 or 0 nodes, then that is a binary tree. Okay, full binary tree, that means every non-leaf node has 2 child node. I will give you some example. We have some examples here later. Okay, so let us go through this. And complete binary tree, a tree is filled top to down and left to right. Okay, so that means we can in other way we can say except the leaf level, which is completed. We'll see some examples. So binary BST has binary SAST. It is common name as BST. Okay, we'll say BST. Okay, so BST has some properties. So the left value is always greater than less than the root value, and right value is always greater than root value. So based on the number of branches and nodes, trees are divided in different types. One of this called is heaps. So in a heap, a parent A heap is a complete binary tree with the example with the properties that its parent is greater or equal to child node. But here in binary search tree, parent is always less than the left tree, okay? And here parent is always greater than or equal to its child nodes. There is APL tree, splay tree, red black tree, B tree. Okay, these are the trees. So mainly, so maybe not in this course, but in our next course, like algorithm analysis course, you will see APL tree, red black trees, and some of these trees also. Now let us go with some example to see more detail about this kind of trees. Okay. Okay, so binary tree, a binary tree is a tree that has exactly either empty or each node has exactly at least two nodes. That means a binary tree in a tree, each node has either 0 or 1 or maximum 2 child nodes. Okay. And full binary tree is a binary tree such that each leaf node has exactly 2 child nodes. I will show you this. With example is easy. So the slide says book has some errors. Okay, so 7874. So please check that if this error exists, then make this correction. Okay, and then you see the binary tree, full binary tree, and complete binary tree. Okay, I will come up with example, then you will see and understand. It's easy to understand. Yeah. So here, the left one is a full tree. That means if a tree has in a tree, every node has true subtrees except the leaf level. So these are leaf levels, so we don't need to anymore. So it is one leaf, this one leaf, this one leaf, and this one leaf. Okay, and in a complete tree, okay, in a complete tree, for instance, this one, you see this one is full tree, but this one is right side is complete tree. What is the difference between this one? So here, so this level is full, this level is full, this level is full, and starting from the left. So here this is full and this is full, and then if there are more entries over here, then the next entry will come here, this side. If then there is another one, then that will go here. If there is another one, that will come here. There is another one that will come here. Okay, it is going to be completed from left to right, Okay, in the definition, if you go to the definition, it says like that. Okay, and it is full. The next one is a full and complete. This one is full and complete. Okay, so this is started from left to right, and you see that every level is complete except the leaf level. So these are little leaves. Okay, we have a few more examples here. So it is a full and also complete, right? Number one. Number A is full and complete, but this B is complete but not full. Okay, and this is neither complete nor full, right? So in order to be is complete, what do we need to do? This one should go on the left. Okay, and this needs to be completed first. Okay, before it go here. Okay, and this is a binary tree. That means a node has 0 or 1 or 2, we say subnodes, right? So this has 0. That means there are no nodes. These are 0. And which have 1, this which has 1, this has 1. Okay, and which have 2, this has 2, this has 2 subnodes. Okay, and full binary tree. Okay, so that full, for instance, here it is, this node has 2, so this is full, it has 1 and 1, another 1, and this is also full, this is 1 left side and this is another right side. This is full. Okay, so it could be full other way. For instance, it could be full like this way, this one, it could be full. Instead of this could come here. Okay, that also could be full. And in that case, you will say that complete also, full and complete also. Okay, and this number C is said that is neither full nor complete. Why it is not full? First of see why it is not full, because here it cannot go to the here unless it complete these ones. B should be connected here. Okay, B should be here, and UV and W, and this one should be W. And the right one, so this is V, this is U, UV, W, and then this one should be X. So this is completed, this is completed, this is completed, and it is W and X, Y, right? X and Y, where Y should go. Okay, can anyone please tell me, in order to make this tree both complete and full, what do we need to do? Still we have,
would we have to add an extra node on W and on the one that's connected to X?
something, let me draw it. Tell me. So here is and T is as U, this and B, and W and X. So like this. And my question is that where the Y should go? But the node Y should go.
Move Y to connect to the node that X is connected to?
No. We need to make from the left. Y should go over here. You understand?
Yes.
Y should go over here. So it said that complete. In order to be complete, start all level and then start from left, go left to right. So then y, this is x is full, right? Yeah, t is full, right? So r is full with this and t, s is full with u and v, t is full with w and x. The y will go the left side of u. Everybody okay? Is everybody okay?
Yes.
So I think reading the book should be fine because you will see pictures and you will read the examples and definitions. Yeah. Okay, one thing remember that binary trees are ordered. The sequence is a matter. So then if we say that A, B and C, the value, and if this switch the value, it's a C and B, these are not equal. Here we say that we know that is a root, a node contains a value, right? And link. So the value is matter. Okay. So the value B and C are different. Or maybe equal. Okay, it also especially in the binary search tree, because we know that definition, according to the definition of binary search tree, okay, the left child, the parent is always greater than left child, and the right side is always greater than its root. So likely we say these are not exactly same. Okay. So then in case of binary search tree, this is the maximum capacity of a binary search tree is 2 to the power n plus 1 minus 1. Okay. And the least capacity is 2 to the power n. Okay, please read the slides and books, and then you will get some quiz questions from the slides, and like these kind of quiz questions. Okay, from the definition and properties. You will get quiz question. Okay. So binary search tree, it has some special properties. Okay, binary search tree, that means, okay, so for instance log or LG with base 2. Okay, it is in a binary search tree, because we know that every node has 2 child, right? Left and right. So you see that there is slide number, you say 1 2 3 4 5 6 7. Okay, so then what is the level for any element or the maximum element? So we can see the level or height. Okay, so here that is 1 2 3 4 5 6 7 elements. So the height will be log, okay, LG log is base 2, okay, 7. So what is log base 2 7? Okay, is 2 point something. Okay, so then if we take int value or if we take floor value, then we will get 2. That means it has 2 levels, 1 and 2, 2 parts. In general, height is called, or if it's depth, on sometimes it's called h, or sometimes it's a k, equal to interval log with base 2m, where m is the number of data element to store in the trees. Okay, so now let us go. So a BST, by looking this formula, okay, for any node with position I, the store left child in position 2i plus 1, and for the right child its position would be 2i plus 2. Okay, for any I, for instance I equal to 1 2 3, whatever you say, for any I we will get the position. The left is 2i plus 1 and right is 2i plus 2. Okay, so please practice this and read this book and read the slides. So these are the foundation actually for other. As I said that for the next 3 weeks we will discuss tree and tree based data structures. So it is very important that you understand and you have clear understanding about this tree, different kind of trees and their properties. So please go through the slides and read the slides, okay? And now the question is that how a tree is implemented. First of all, it is said that a tree has a special kind of connection links between the nodes, right? So the easier way will be implemented as a linked list. So as a linked list, since a root will have maximum 2 children, we are discussing a binary search tree, okay? So then we will have a left. So then each node will contain 3 things: data, left pointer for the left side, left child, and the right pointer for the right child. Okay. And this is the important thing, that how do we traverse. So we travel through a BST. Okay, so a BST mainly 3 elements then, right? We have root, left child, and right child. Root, left child, right child. So based on the position of the root node visited, or based on the sequence of the root node visited, there are 3 types of traversal. Okay, one is called pre-order traversal. That means you will visit the root first, then left subtree, then right subtree. This is the fashion. You will start from the top of the tree, and then you will then go to left child, left subtree, then right subtree. Or in order traversal, you will visit the left subtree first, then right root. That means in order means your root will be in between left and right child. Okay, and then post order means your root will be after left and right side. Okay, that the root will follow left and right side. So one thing is that we see over here, you see that right child never goes before left child. Right child never goes before left child. Always left, right. This sequence will be maintained. Okay. It is in general said that we can say that your elder brother cannot be younger than you, right? So even there are twins, some twin brothers or sisters, even they are different by a minute. Okay, by the time stamp born. Okay. Okay, and there is another kind of traversal. It is called breadth first traversal, and there is another kind one. It is called depth first traversal. Okay, so breadth first traversal means level by level. So what is meant by level by level? Okay, we will start from one level and we will finish all nodes from these levels. For instance, this is root level. We will start and end root level. There is only one element, so it's this element. Then here we will start all elements in this level, and then we will start from here. We will go all these on 3 and 9, and then here next level we will start from here, or we will go 1, 4, 6 like this way. Yeah. And this is called breadth first, and there is another one. It is called depth first. Okay. Okay, we will come with some examples, but here what we have is these are called depth first. Okay, depth first traversals. Okay, are recursive process, and based on the position of root level, root node visited. Okay, so these are there are 3 kinds of depth first, and the breadth first is only one kind. The total, how many orders are there in tree traversal? How many kinds of traversal are there? Who can tell me?
Is there 4? 3 in the depth first and 1 in the breadth?
Yes.
Breadth first.
Yes, you're correct. Breadth first is only one kind. Okay, and the depth first is 3 kind, total 4. And one thing is that, always remember that when you are traversing a tree, you cannot go from right to left. Always from left to right. Okay. So never you can visit right child first and then left child later. That will be a mistake. And there are some slides. Okay, so please complete these slides with this. Then visit means the root first. Okay, and then left right. The left visit or vector, whatever you say, the root, because the left and right they denoted by R. So this is why right is denoted by R. This is what they call V. Or you could say O for origin. Okay. So please complete this, okay? And please let me know if you find any issue. Okay. you will see the sequence will be different. So in your test, you will be given some trees. Okay. You will be given some trees, and then you will be asked to write the sequence of depth first. So these are three kind of depth first, right? Traversal. Then just three kind for this and three kind. So please try to understand this, okay? Now the breadth first. So we saw that there is only one kind of breadth first, right? How many types of breadth first process are there? Only one kind, right? So breadth first traversal is to visit the nodes level by level. What is mean by level by level? First visit the root level, then the wall children level, then from left to right, then grandchildren level from left to right, and then maybe if there are more grandchildren, then go from left to right. So starting from A, then we will see B and C, then we got D, F, G, H, A, B and C, D, F, G, H, and I, J, and K. Okay, now since it is a BST, it's a binary search tree, this value has order. This value are put in order. So here you cannot say I cannot put in any order. It's okay. So now one thing is that this is not neither a complete binary tree, or this is neither a full binary tree. It is neither a complete binary tree nor a full binary tree. Okay. So how the order will go? So simply what you can do, for your understanding, you can draw a line. So you will start from E, so A, and then B and C, B and C, D, F, G, H, so D, F, G, H, and I, J, K, and I, J, K. For instance, it could be something like this. If we take up this, then it could be K over here. It could be K over here. Okay, does anyone has any question?
No.
Okay. So, next lecture we'll see actual programs, how to develop BST, binary STSG, and you have like breadth first algorithm here, and we have traversal, other kind of depth first traversal algorithm. Okay, and let us see what do we have. Deleting nodes from a tree and then inserting nodes. Okay, so we will discuss this in our next lecture. So if you are familiar with Java, BST, So binary search example with C++. Binary search, okay. Okay, BST implementation actually I need. Okay, not binary search. Okay. So this program has BST implementation and traverse node. So in order, pre-order, and post-order. That is the depth first searching. Okay, and this is the implementation of this. This is insertion and deletion. So I would like to give you this program if you are familiar with Java. Then you can practice this program quickly to get some idea. In our next lecture, we will discuss, we will convert this program in C++. Oh. Let's not find our last lecture video. Let's see. I have also this one in C++ with C#. You may practice this one, BST implementation example 1 with Java and with C#. Then if you read this is straightforward, then there is no pointer in it, and then we will discuss this, how to implement, convert this program with C++. So that's all for today, and then we want to stay here, and then please read the book, whatever we discussed so far. At least please read the book one time, then it will be easy for us to go through with the next topics. Here, let me take the attendance today. Today is 18, right? 19. Okay. And Jason?
Here.
Matthew? Daniel? Myers? Mary?
Here. Here, sir.
Okay. Antonio?
Here.
Jasmine?
Here.
Trayton? Alisa?
Here.
Taylor?
Here.
Ernest? Angel.
Here. Ernest is here. Ernest is here.
Angel. Jordan.
Here.
Cody. Isaiah. Savvy.
Here.
Loyal.
Oh, here. Savvy's here.
Jimmy.
Here.
Loyal. Dave.
Present.
Karen. Mikhail.
Here for Mikhail.
Jess. James.
Here.
Brandon.
Here.
Noah. Alan. Kenya.
Here.
Jimmy.
Here.
Lilivia. Jesus. Cameron. Sebastian.
Here.
Alec.
I'm here. Hey, Lowell said he was here too.
Who?
Lowell, he said he was here.
18. Line 18.
18?
Yeah.
18, right? This one, right?
Yeah.
Justin. Justin Walls. Daniel. Andrew.
Here.
Nicholas.
Here.
Jessica. Okay, so and I will upload a quiz. Structure, okay? From the previous week and this week.
When's the quiz
And
due?
sorry,
When is the quiz due?
so next week. We will have total 5 to 6 quizzes. So next week we have 3 is completed. Okay, does anyone has any question?
No, no questions.
Okay. Then that's for today, and then thank you so much. I will see you day after tomorrow.
Thank you.
Bye bye.